So what is hyperparameter here? So till now that we have seen the matrix, recommender matrix that we have built A. In this matrix that we have seen that the matrix, the dimension of this matrix in general we got n cross m. In n cross m. This n is responsible for number of users. Already we have seen this is for user 1, user 2, like that up to user n. And this m is responsible for number of items I1, I2, like that up to IM. Okay. So the common element, general element that we have taken here, Aij. It's a general element. Okay. So, and after using the matrix factorizations, we have seen in one of our previous video, we have seen this A can easily be matrix. If we matrix factorized it be into such kind of C transpose. Okay. And the dimension of this matrix is here what? N cross M. And the dimension of this matrix B is what? N cross D. And the dimension of this matrix is transpose is what? D cross N. Since the transpose matrix dimension is D cross N, then we can conclude that the dimension of the matrix C is what? N cross. And this matrix B matrix is responsible for features vector of each user, and this C matrix is responsible for features vector of each. Sorry, it will be n mm. Sorry, it's my bad. It's m cross d. Okay, this matrix is responsible for features vector for each users. Is user, and this C matrix is responsible for features vector for each item. Okay, this is the that, and the thing here, the hyperparameter here is the dimensions. It's out it we can easily find how many users we have, how many items we have, but the d is totally unknown to us. So here d is the hyperparameter. Here d is the hyperparameter, means the what will be the dimension of our features vector. That's the hyperparameter. The main job is we have to choose this correct d value to find our correct accuracy of our problem. Okay, we will see these things how to choose this one. But here d is the hyperparameter. Here d is the hyper. So d value will be must be greater than 0, and d must be less than equals to minimum of n and m and n. Okay, that's the thing. Okay, the first one is the how to choose this value. What will be the correct value of this d? That's the first thing. So that this d is depends on the problem specifics, or what is our task. According to that, we have to choose. So that this d value will be depend on the first problem. It's the problem specific. Is the problem specific, or what kind of tasks we have. Okay, problem specific. So means it depends on our situations, which situations, what kind of situations we have. Okay, so what kind of accuracy we need, but there have some relations to the accuracy, and this D. But first thing that first it's depend on the problem specific, what problem we have. Okay? According to that we have to. The second, it means the general purpose means. The second is method is a systematic way they have to choose this DOI. The systematic way that we have. So let's try to understand this systematic way how. So what is our actually the optimizations problem? If you just remember the previous lecture, what is the optimizations problem? So the mathematical optimization problem that we got. What is this? Just remember in yourself. So the optimization means we have to find we have to approximate this matrix as a factorized of this term. Since our main job is we have to approximate this matrix as this term B into C transpose. So means at the end of the day we have to minimum, we have to this distance we have to minimize this Aij. If Aij is the common term and Ai minus Bi transpose Cj. If Pi is the ith column of the B vector and Cj is the jth column of the C matrix. Okay, just write it. Bi is the ith column of B and Cj jth column of the C. That is the means that this matrix means is the general form of. So we have to minimize this term. We have to minimize this square. It will be summations over ij overall ij. Okay, and the arg mark mean that we have to interest to find. The arg mean is B comma C. Okay, and these things are called this function, that is the loss function, or you can treat this as a square loss. This is like of a square loss, or you can treat these things as an error function. Error. We have to minimize this zero term. That is the job that we have to see. We have generally seen this is the error term. So the relations of this error term and this dimension of this is like that. So if we increase the the error that we got is equals to ijth value ai comma j minus Pi transpose Cj is square. Okay, this is the error term. So the relations is look like that. If we increase the value of d, that implies that the error will decrease. Error term is decreased. Okay, so this concept, if you write this concept, okay, in a limiting form, if you write this concept in a limiting form, limit d tends to infinity. When d tends to infinity, then this term ij minus Bi transpose Cj whole square. This term I am actually talking about. Let's take it this back. It equals to 0. This is the limiting concept. The main same concept. If we increase the d value, then error will be decreased. That is the concept. So just try to plot it. If we plot these things in a diagram, then we can see it is the d value and it's the plus infinity. And if it is a error term, then in generally we have shown this kind of picture. We got this type of picture. Means when we increase the value of the d, so the error term will be reduced like this kind of picture. Okay, so the thing is that we have to remember here the slope of this error term. Okay, so here d somewhere here, suppose let somewhere here d, if we consider somewhere here the d value, somewhere here suppose let's take somewhere here it is the d dashed value. Okay, if you consider this region, if we consider this region, then the error here, the error that reduced here in this region, the error is reduced very fast, but in this region you have shown the error is reducing slowly. Okay, the first concept is here error is reducing very fastly, but here the error term in this region, the error is reducing slowly. Here error is slowly. I think its spelling will be slowly. Okay, and this point, that point where the reducing of the error term will be more slower, this point actually called the point of inflection. This point is called the inflection point. This point is actually called the inflection point. Okay, so here what will be the d, the point, that the inflection point, what will be the d value, that will be our the d test. Okay, so the d, the d value that we have to choose commonly, that d will be the value at the inflection point. This value we have to choose the d means at that point what will be the. So if you just see this picture through like in a derivative form, I think it will be better for you easily understand. Okay, so just instead of using the error term here, if we use the derivative, means how much rate of the change, means I'm interested to find its slope value. Okay, what will be the slope of this point? What will be the slope of this point? What will be the slope of this point? So just see the slope value. In this region, the slope will change, the slope is changed dramatically, but here the slope is not changing so much. So if you just plot this picture to the slope, I think it will be better for us for easily understand. If we write these things in a like that way, this axis is simple, the derivative of the d, del d, and here it is the del of error term. If these things happen, then the picture that we got here. So here these are somehow this point. Suppose like somehow this point here. So first thing, that how we'll calculate it, these differentiate value, how we'll calculate it, this value will be calculated in a like this manner, so the del of error by del of d will be the differences of the error of the d1 point minus the error in the d2 point, where d1 minus d. That's the thing that we have to always remember. Okay, so we in general, if we plot these things, we will see in these regions, means if we somewhere here these regions, so in such regions the it's changed dramatically, but after some time it's not changed, it will be like constant. So we have to choose such regions like somewhere here, somewhere here we have to choose, somewhere here. Okay, this is the point of the inflection, this is the inflection point. Inflection point. Okay, somewhere here. These things actually we have to plot. Okay, I think you got the idea how to choose this in the systematically way, how to choose it. If we simply plot it, the point that we have to choose, so simple inflection point. So in inflection point, the changing of the d will not be so much. Okay, so that after this inflection point, the changing of the error term will not be so much. So we have to choose like in that manner. We have to choose this hyperparameter, and generally we will choose in this according to our problem. But if you just use a systematic way, then by simply using this optimization problem, we have to choose this. Okay, by this minimizing this error. Okay, I think you got the idea how this hyperparameter is important to this recommender system class.